if we were asked to find the derivative of this big, ugly thing, how could we do it? We could use the product rule, but the product rule for 4 terms is a bit complicated. Not complicated, it'll just take a long time. We can try distributing some of those terms, like distribute this into this one and this one into this one, but you also have this cubed here, so that's complicated. What we're going to learn in this section is how to do logarithmic differentiation, which can actually simplify this problem. Because logarithms, remember a property of logarithms is that the log of xy, two things multiplied, is just equal to the log of x plus the log of y. So we can actually just break this big ugly equation down into 4 separate things that we can essentially add if we're able to take the log of this whole thing. The problem is that we need to know how to take the derivative of that thing with the log in it. So that's what we have to do here. So if you look, the way this is going to look, if we take the log of both sides in that equation, we're going to have log of f of x is equal to, and it's just going to be those 4 things multiplied, right? Or added, I should say. The log of x plus 2 plus the log of x plus 5 plus the log of 2x plus 2 plus the log of 3x minus 3 cubed. And remember, we can move that, another property of our logs is that we can move that 3 down in front of the log. So this actually looks pretty simple. We've just broken it up into a bunch of separate logs. And if we could take the derivative of those separate logs, we could take the derivative of the whole thing. And that's what we're going to do. How these derivatives work, starting with the natural logarithm. Remember, that's a logarithm with base e. The derivative of ln x, which is the natural logarithm, is just 1 over x. Super, super simple. Isn't that crazy? That a bit of a complicated function, the derivative of it is super simple. And logarithm, general logarithm, so when the base is not e, it just looks like this. So it's like 1 over x ln k, where k is the base of whatever that is. This sort of mimics how exponentials work. If you take the derivative of an exponential that doesn't have a base e, you have to multiply by ln of the base. And that's the same thing here with logarithms. You have to multiply by ln of the base. So let's see how this actually works with some examples. So y equals 3 ln x. Well, we know we're looking at the derivative of the natural logarithm, which the regular derivative is going to be 1 over x. But we have a 3 in front. So essentially that 3, so y prime equals, 3 is a constant, so we can just leave it out of the derivative. So it's basically like saying 3 times the derivative of ln x, which is just 1 over x. Or we can just simplify as 3 over x. Not more complicated than that. Okay, b. This one, we have the derivative of log base 10 of 5x. So the thing is, we have a function inside another function. The 5x is inside that whole thing. So we are going to have to use chain rule here whenever we have a function inside a function, right? So we can start off the same way. If we call 5x u, right? We can multiply, essentially the derivative is going to be dy by dx equals dy by du times du by dx, right? And if 5x is u, du by dx is just going to be 5, right? The derivative of 5x is just 5. So we just need to find the derivative of y with respect to u. And that's just going to be basically f prime of u, or the derivative of y with respect to u. It's just like if we replace that with a u, right? And the derivative of that is just going to be, if we look at our pattern from above, it's just going to be 1 over u, essentially, that thing in the bottom, times ln of 10, right? So our entire derivative, dy by dx, is going to be 1 over u ln 10. I'm going to replace the u again with the 5, so 5x, I mean. So 5x ln 10 times 5. And you'll notice here that 5 is going to end up canceling out, and what we end up getting is just 1 over x ln 10. That's our derivative of that function. Sort of interesting that that 5 canceled out with that 5, and you'll see that happens quite a bit when we take the derivative of logs. Also notice, before we go to the next question, if you can identify the pattern, essentially the chain rule is the same shortcut that we used last time for the chain rule for all the other rules, is that essentially what we're doing is we're taking the derivative of the outside function and multiplying it by the derivative of the inside function. So we can use that to answer this question a little bit more quickly and efficiently. So how to do that? G prime of x. Well, if we think about what the derivative of the outside function is, it's going to be log 2 of whatever is inside, right? And the derivative of that is 1 over 2x plus 5 times ln 2, right? And then all we have to do is multiply this by the derivative of the inside function, which is just 2. And that's essentially our answer. I'm just going to simplify it a little bit. 2 over 2x plus 5. There should be a plus sign in there. Plus 5 ln 2. There we go. That's our derivative. So now let's go back to that question from the first page. In order to take the derivative, let's try taking the ln of both sides. Now we could take the log or the ln of both sides. We know the derivative for ln is easier, right? So let's take the ln of both sides. So ln f of x equals ln x plus 2. And I'm just going to write it like this. I'm going to separate them right off the bat. Plus ln x plus 5 plus ln 2x plus 2. And then again, the 3 comes down in front for this one, right? 3 ln 3x minus 3. Okay, so now let's take the derivative. We'll worry about what the left side looks like in a second. Let's just take the derivative of the right side because that's not too bad. So the derivative of ln x plus 2 is going to be 1 over, essentially, x plus 2 times the derivative, it's the chain rule, right, times the derivative of what's in the brackets, which is just 1. So we're good there. Plus 1 over x plus 5 times 1, which is the derivative in the brackets, so that's fine. Plus 1 over 2x plus 2 times the derivative of what's in the brackets, which is actually 2. So this on top, I'm actually just going to change that to a 2. And then the derivative of this one is going to be 3 times the whole thing, so it's like that 3's on top, over 3x plus 3 times the derivative of what's in the brackets, which is times 3. So I can actually simplify that, that last one there, and I'll do that in the next step. But realize what we have now. That derivative was not too hard to take. It would have been a lot more tedious to take the product rule of everything, right? Now, the problem is the left side. The left side's a little bit different because usually when we take the derivative of something, we're taking the derivative of something that looks like this. Y equals something, 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 something. So when we take the derivative of it, it looks like this. dy by dx equals something else, right? But in this case, we don't have this side in terms of y, right? We have it in terms of ln of fx. We can actually, if I want, I can write that as a y there. So it's a little bit easier to see. So essentially what we have, instead of this over here, we have a ln y that we're taking the derivative, and that's equal to something. So the right side is okay, but the left side, how do we do that if it doesn't look like a regular function? Well, the key is here, we have to use the chain rule actually to evaluate the left side as well as the right side. So the right side we're good with, but the left side we have to use the chain rule. What's the derivative of ln y? Right? Because we don't have it in terms of y, so we have to actually take the derivative of that. It's sort of like saying we're taking the derivative of both sides, and the right side's not the side that's the problem. The left side is. So to take the derivative of this, we're going to have to use the chain rule, because the problem is we're finding the derivative. We want to find dy by dx, right? So we want to find the derivative of y in terms of x. But if you look here, there is no x there, right? So how do we do that? Well, remember, the y is just a function that contains x's in it. So the derivative of y by itself would just be this. But the problem is we have this outside function here. We know how to deal with this, though. So essentially what we're going to do is this. The derivative of ln y would just be 1 over y, and then using our chain rule, it's going to be the derivative of whatever's in the brackets, and whatever's in the brackets in this case is y, and the derivative of y we just call dy by dx. So essentially we just use the chain rule on the left side to come up with that, right? So it's the derivative of y, the derivative of the outside function, which is 1 over y, times what's inside the brackets, which is dy by dx, because we need to always multiply by the derivative of what's inside the brackets according to the chain rule. So that's actually what the derivative of that left side looks like. 1 over y dy by dx. And just going back here. So this is 1 over y dy by dx, according to our chain rule. And then, since this is sort of ugly, we want to bring that y to the other side. We basically want to find the derivative just by itself, right? We want to isolate that. So dy by dx is just going to equal, I'm going to put this all in brackets, 1 over x plus 2, plus 1 over x plus 5, plus 2 over, well, a lot of those 2's are going to end up canceling out, right? So I'm just going to cancel out those 2's essentially. So it ends up being 1 over x plus 1, and then plus, and again, this 3, 3, and 3 are going to cancel out here, or they're going to simplify. So I'm going to go 3 over x plus 1, all times, if we cross multiply that y from this side to the other side, all times y. And we already know what y is. Y is essentially this whole function, right? But that's our derivative. So I could plug in this whole function as the y here at the end, but I don't want to do that because it's going to take up a lot of space, and essentially this is the derivative, right? So in a lot of ways this is simpler than using the product rule, but it also ends up with a quite a big answer here. If you just wanted to plug in a value though, to find what the derivative was, say at x equals 3, this would actually be pretty easy to do, right? You just plug in the x's as 3, you plug in what the derivative at 3 would be here, and just plug that in for your y value, and there you have it, okay? So just taking a step back, the reason why we use the derivative of logs or ln is because it can make multiplication or division questions actually much simpler to take the derivative of. So let's try this question. Differentiate the following. Ooh, that's a little bit more ugly if we had to use product rule and quotient rule here. So again, let's try by start by taking the log of both sides. So I'm going to call it ln of y. I'm going to just replace f of x with y. And then here, it's the same idea as before. So we're going to have ln of x to the 4 plus 1 plus ln x plus 2 to the power of 1/2, right? That's really what the radical means. And then if you remember our laws of logs, when we have something in the denominator, it's like we're subtracting that. So it's going to be minus ln of 2x squared plus 2x plus 1. Right? Now, one thing to simplify, I'm actually going to take this 1/2 and I'm going to write it down in front. Right, just to make it a little bit simpler. And now we could take the derivative. And remember, we have to take the derivative of both sides here because it's not explicit in terms of y. So the derivative of the left side is actually going to be the same as it was in the previous question. It's going to be 1 over y, because that's the derivative of ln y, times dy by dx, according to our chain rule, equals, well, this is going to be 1 over x to the 4 plus 1, times the derivative of what's in that brackets, which is going to be x cubed. And I'm actually just going to replace what's in the numerator. If I erase that, I'm going to replace what's in the numerator with x cubed, just to make our life a little bit easier here. Plus 1/2, so that's just going to be like this, 1 over 2 x plus 2, times the derivative of what's in brackets is just 1, so we don't need to worry about it, minus the derivative of that's going to be 1 over 2x squared plus 2x plus 1 times the derivative of what's in that bracket. So again, I'm just going to replace what's in the numerator here, because it's just going to be multiplied anyways, by what the derivative is, which is going to be 4x plus 2. There we go. That's our derivative. And again, to make it explicit, dy by dx, I need to cross multiply that y up there, right? So it's going to be x cubed over x to the 4 plus 1 plus 1 over 2 x plus 2 minus 4x plus 2 all over 2x squared plus 2x plus 1 all times y. There we go. That's our derivative. Okay, now this is a little bit of a different question because we have an exponent that is it's a variable, right? So we have a variable that's down here and a variable that's up here. So it's like an exponential equation, but it's also not an exponential equation because it has a variable here. So it's a combined exponential equation, sort of. And there's a few ways to tackle this question, but I think the easiest way is let's make that exponent x, let's bring it down. And the way we bring it down is by taking the ln of both sides, because we're just going to end up with x ln x squared plus 3. Right? So again, taking the derivative of the left side is going to be 1 over y times dy by dx equals, and we're going to have to use our product rule here, right? If this is f and this whole thing is g, we need to take the derivative of the first, which is just 1 times ln x squared plus 3, and then plus the first, which is x, times the derivative of the second. And the derivative of the second is just going to be times 1 over x squared plus 3 times 2x. And we could just simplify this whole thing a little bit. So ln x squared plus 3 plus, and that numerator simplifies as 2x squared, right? Over x squared plus 3. And then to make it explicit in terms of dy by dx, we can multiply the whole thing by y. Which, you know what, in this case, because it's a little bit of an easier one, I'm just going to write it out. Because y is just x squared plus 3 to the power of x. So there, that's our derivative, all in terms of x. There we go.